We are going to continue on with our topic on advanced technology for precision IPM. We've got one more presentation on examples. So Manoj Karkee from Washington State University is going to talk to us about UAVs. So there's going to be a little overlap, but that's okay. And then after that, we're going to get into more of the regulatory aspects. And we've got two individuals here that will talk about that. So I'm going to ask Manoj to come up. And again, the questions that you all have, we will be we'll be addressing those at our Q&A session after our last speaker. So hold those and ask them at that time. So, Manoj.
Thank you, Steve. Hello. All yours. Thank you. Well, thank you, Steve, for the opportunity. And as Steve pointed out, there may be some overlap. Okay. So there may be some overlap, and basically, looks like I'm going to summarize some of the stuff that was discussed in the morning sessions, including Dr. Kinzile, Dr. Park, and Dr. Abhijit Chaudhary. I forgot full name looks like. But anyway, I'll still go through it, skip when needed. And there may be a few examples which may be newer than what was presented. Towards the end, I'll also briefly introduce the regulatory side of the UAV authorization, but more discussion on that is following up, so it's not that much there. This presentation was contributed by Dr. Lovecoat, Dr. Lichman, Dr. Shankar, Dr. Taylor, Dr. Chinjang, all from Washington State University Center for Precision and Automated Agricultural Systems. We're also affiliated with the Biological Systems Engineering Department there, at least most of us. So before I begin, I wanted to spend a minute or two on talking about CPAS, the Center for Precision and Automated Agricultural Systems. This is the transdisciplinary center located in Prosser, Washington. About 15 plus faculty members from many different disciplines, including biological scientists, physical scientists, extension educators, economists. It truly provides an environment for or facilitates a collaborative research in this kind of work that I believe is critically important for the type of problem we're trying to address in a lot of high-value crops. Some of the projects, major projects that this center is working on, including myself, I'm lead on most of these, at least half of those there. Apple and cherry harvesting, apple and raspberry pruning, intelligent bean transportation system for orchard application, water and nitrogen stress sensing, weed control, all those including UAS for production agriculture. There's some of the larger projects or areas of research that we as the center are working on. Today certainly we'll be talking about UAS and some of the work we're doing, including some of the work that is being conducted outside of WSU. So this first of few slides may be just too simple for some of us, or most of us, talking about what UAS are as a kind of a background. We call it unmanned aerial systems. We also sometimes use unmanned aerial vehicle, drones. Oftentimes, at least I would think of unmanned aerial systems being more of the system with ground control, payload, sensors, data collection, processing, storage, distribution, all these facilities or the other infrastructures put together, including hardware platform, gives us this unmanned aerial system. particularly for the applications and the type of applications we are interested in agriculture, including pest management. In terms of scale or the size, let's say it varies from really tiny insect size, robotic platforms, to all the way to the type that Dr. Giles presented this morning, and those ones used in defense, tens of billions of dollars, maybe tens of millions of dollars, or maybe even hundreds of millions of dollars, versus maybe a few $100s, even less. So that's the range. But in terms of agriculture, we're more towards this left-hand side of the size. We are even more interested in those small UAVs defined by FAA, which are less than 55 pounds in their total weight. Last year or the year before that, this organization called Association of Unmanned System International. Yeah, I think that's what it is. They published a report talking about the growth and potential growth in UAV industry for next few decades, I believe. The interesting point indicated there was that DoD is spending much more in unmanned systems these days compared to even a decade ago. We can see the numbers here from a few hundred millions to a few billions of dollars. More interesting projection here, as we can see this rate, maybe this area, agriculture is leading the civilian utilization or application of UAVs or UAS going into the future, and that's really promising. In terms of this economic impact, Washington, California, and Texas are some of the leading states as projected there, and really, really critical numbers here that shows a really good promise in terms of where we're going. Pretty much the same thing I'm talking about here, but one of the critical kind of phrase that I'm using here is resolution. Plant-by-plant resolution. Again, this is the discussion we already had in the morning as a summary again. This kind of technology provides us more or higher resolution in both temporal and spatial scale compared to manned or satellite remote sensing systems. And that's the advantage added to US systems. And that allows us to do plant level management, and I believe that should be the future in terms of precision agriculture, remote sensing, and other precision agriculture related systems. A few examples that I wanted to present from the work we as a center at Washington State University are doing, as well as a few other ones, examples from around the country. But before that, in general, what are the interests in pest management when it comes down to using UAVs? I kind of prefer to divide applications into two areas. By passive, no means it is a passive application area, but what I mean is that we're more into collecting data, monitoring, scouting type of applications, versus by active, I mean more into the applications of products, doing something physical with the flight itself. Precision chemical application board deterrents. And again, we are more interested towards mid-size and smaller to mid-size UAVs in agriculture, low-cost platforms. That low-cost aspect is important because UAVs should provide data and services, or whatever those applications we're doing should be cheaper than those with manned aircrafts And then only it makes sense for growers to move towards this technology. Some of the ongoing engineering efforts in applications of UAS include validating applications with proven values, in my opinion. For example, color and NDVI maps. Whether it is unmanned or manned or satellite imagery, we have been using NDVIs for several decades now, and it has proven values to growers and researchers. With UAVs, different types of UAV platforms, we're trying to pretty much validate that same thing. We're showing we can do it with smaller, lighter, unmanned platforms, maybe even adding economic value into it, making it cheaper, faster. But in terms of technology or the tool itself, it was used in the past and it is proven. Plant stress maps, developing different types of stress maps. For example, weed density map or weed presence absence map, whatever those stress maps are, those were developed using different technologies in the past. We're doing the same thing with UAVs. Precision chemical application, we're doing that with manned aircrafts. We're doing that with boom sprayers. We want to do the same thing with UAVs. Again, it has values. We saw that again in this morning. Some of the new areas may not be really new, but we are also interested in looking into new applications that are possible with the type of resolution, both in spatial and temporal dimensions. For example, identifying new particular diseases. For example, citrus greening disease, bird deterrents could be another applications where we could apply these new tools. Can we do bird deterrents with manned aircrafts? Maybe. But again, there are advantages of using UAVs. More into the technology, the system side, we are talking about increasing stability, endurance. I'm not sure if we spoke about endurance in the morning discussions this morning, but that's really critical, important aspects when we talk about UAVs. We're flying 10 minutes oftentimes, 15 or a few hours, but that may not be enough in a lot of applications we're interested in. Improved image staging, new data mining techniques. As we're gathering more data, there has to be better, more efficient ways of finding out or converting data into information. So just to summarize remote sensing with UAS, we have possibilities with fixed platforms, ground vehicles, satellites, aerial system, manned or unmanned, but there are some critical advantages of using UAS. Again, we discussed that a lot in the morning and in earlier slides too. When it comes down to crop monitoring for pest management, we're looking at canopy variability maps, stress maps, monitoring effectiveness of pest control strategies. For example, we found some problem, we applied some chemical. Is that chemical working? Is the crop recovering? How fast it is recovering? So we can go back, revisit the site, take those images, monitor the situation. Real-time monitoring for field management is more towards, I have a cool device, I'm a farm manager, let it fly, come back with color images. Just use that as a tool rather than driving there in my four-wheel drive trucks, spending hours and hours in driving into and back from the field. Can I just send a UAV, take whatever needs to be taken? As simple as that. And there are potential, some of our growers indicate that there is a potential to increase the efficiency of farm managers, field managers by as much as 50% just by doing that. It has no kind of data processing technology embedded in it. It's just raw images that these guys may be looking at. So let's talk about a few examples in both the what I call passive applications as well as active applications. Let's start with passive. Detecting vine vigor is one of those applications that some of us at WSU are working on using unmanned aerial UAV-based images and applying some image processing techniques. Again, we're not going into details of those techniques. Oftentimes, those are standard techniques of thresholding using color or infrared data. Other times, it is calculating NDVIs or some other vegetation indices, which is standard procedures that are out there. There may be some image enhancement, some color transformation from one space to the other, more generic image processing, machine vision algorithms. We're not going into that, but bottom line, there are ways we can differentiate how vigor the vine is based on the images collected from UAVs. And that can be linked to various things. Is it a nitrogen issue? It is water issue? Is it the cultivar itself? There could be some other problems with that, but again, it gives us the differences. Another applications some of our colleagues at WSU are working on is monitoring subsurface micro irrigation. So they're developing a new way to apply water, and there we are monitoring with UAVs the differences between conventional drip irrigation as well as SSMI-based application. Again, we're using reflectance and we're calculating indices, trying to see the differences. I'll talk about the limit we have with that and the future direction to make more sense of what we see with these reflectances or the difference in reflectances. But that's what is possible with these sensors right now. One example from Florida with Dr. Isani and Garcia Ruiz, SLV disease detection, or citrus greening disease detection with this hexacopter. As we can see, they were able to find most of the trees infected with the disease. It's no news anymore that this disease is really devastating down there, but this kind of technology is helping out to some extent. One of the projects I'm leading at WSU is in the area of bird deterrence with UAVs. Given the size, the maneuverability, and the flexibility of these kind of platforms, the ability that we can program them to make any path anywhere, I believe it can chase these birds away. Not reading these numbers, which shows really critical value for this kind of work, because what we have done in the past is using nets to be effective, but it's really costly. Anything other than netting, for example, using predator birds or sending out high school students to shoot the water guns or whatever those other techniques are, they're only marginally effective. And sometimes growers are losing as much as 30, 40, 50% of their high-value crops to migratory birds. Can we do with UAVs? That's our goal here to understand. We did some preliminary work at Oregon State University with our collaborators in 2012, I believe. Results were not conclusive because that particular year we had funding and we went 10 times in the field. No birds were there for that particular window. So that's part of it. We also had limited experiment set up, so we couldn't conclude anything. But more work is going on at WSU with both fixed wing as well as multi-copter type of platforms. And we believe there are advantages of both of those, and one may be more effective than others as we continue the work. Another more active application of UAS is in cherry drying. After the rainfall, If the cherries are not dried, they will crack, and we're going to potentially lose a lot of crop to rainwater. So this work focuses on sensing the wetness and feeding that information back to a UAV, and then fly it over to dry some of that rainwater in a control loop, so that we do that only when necessary and only to the extent it is necessary. This part I'm not talking about much because Dr. Kenzile again discussed a whole lot in the morning. But one plot I found in the internet from Japan was really interesting. It looks like the registration of this kind of platform has increased almost exponentially over the last decade or so in Japan, and substantial amount of chemical application in rice planting and some other planting is being done by this kind of platform. And UC Davis work that we saw in the morning. Found this from one of the websites. I don't know if it is from Dr. Kenzile himself, but this looks really interesting application in Napa Valley. I'm not sure, is there any timer somewhere? Okay. Technology development side, I discussed a little bit earlier, but more specifically, there are some of the work in the engineering colleges and departments in the area of platform stability, weight, and speed. Another area of research and development that is ongoing is in the area of multiple vehicle utilization to do something. For example, if it is bird chasing, we may end up using 10 UAVs at the same time. There needs to be coordination, collaboration with those platforms. It is also that way because one platform with current battery technology is flying for, let's say, half an hour. We need continuous presence in the field. So one may be coming back for recharging. We'll talk about that a little bit too. But there will be multiple vehicles flying simultaneously or in sequence. So there needs to be that collaboration, cooperation among them, and need to be studied to optimize that. Feet size optimization, how many do I need? 10, 20, 15, 5? That kind of research. Endurance, again, is critical aspect of our ability to use UAVs. How can we increase it? Charging station. There has been work in automatic battery swapping. There is a charging station. Batteries are being charged continuously. UAV can come, dock in it. Batteries are automatically removed and replaced, and then it will fly again. New power sources like hydrogen fuel, which has ability to, with a little cell, ability to power these vehicles for as much as 20, 24 hours, rather than half an hour flight. New sensors for agriculture. Well, certainly there are tons of sensors, but we are now looking at 1 pound payload, 2 pound payload with 5 channels, 6 channels. We would even like to have 100 channel, more towards hyperspectral imaging if possible. Can we develop lightweight hyperspectral sensors? Can we make a 10 channel multispectral sensor still is 1 pound or less? I mean, those kind of technologies are being developed, and needs to be there needs to be more work in that area. I already discussed this concept here. One of the work published by Tusods, I'm not sure how to pronounce. One of our colleagues at WSU and his team is working on liquid hydrogen fueled UAS. This is the platform they developed. They're trying some field work with this kind of platform, Again, it is powered by a little hydrogen cell, and it can run up to, at least if I understand it correctly, many, many hours. So with that, another 5 minutes or so, let's think towards future. What these technologies are capable of and what we need to do as researchers from all different disciplines. Core artificial intelligence, machine vision, autonomous machinery side of research, as well as applied research in the field. Data versus information. This is a chronic problem, in my opinion, for precision agriculture. We have a lot of data, tons of data from tons of different types of sensors. But in my opinion, we're not always converting that into actionable knowledge. Or it's not, there is no easy way to do that. That is robust and can be used by across different applications. For example, we saw this morning from Dr. Raz Khosla talking about decision support system for corn production with several layers. That is the type of work we need to do in many different areas and be able to convert that a lot of data we have collected now and with new sensors, higher resolution sensors, what we can do with that. How can we go beyond differences in its spectral signature? Again, I see NDVI, I see differences. I know we have done a lot of work. There are some successes. We may be able to identify specific stresses in some cases. But in my opinion, oftentimes, stresses are compounded. I have maybe some water stress, some nitrogen stress, some disease stress, insect stress, some of them happening together. Do we have enough knowledge to reverse engineer the differences in spectral signature and actually tell us that 50% of this problem is by this problem, 50% of stress is by that problem? So there has to be work in that area. Identification of stress and do something about it, because we want to link that to, I have the data from UAVs, shows me stresses. Do I have enough standardized way to link that to John Deere boom sprayer to apply chemical where it needs to be and not apply where we don't need it to be applied? Internet of Things, new terminology in agriculture. This has been there for long in the artificial intelligence, computer science discipline. We have sensors everywhere now. Can we integrate them together and make decisions? Again, it goes back to converting data into information. But there is a lot more connectivity now, a lot more devices connected somehow through cloud. Can we utilize that capability, infrastructure, to do better about decision making? Innovative applications. We want to think a little bit beyond perhaps just looking at the differences in spectral signature. Is there something else we can do with this kind of low-cost, flexible, accessible device? Well, precision pollination, there might have been applications in that area, but at least I didn't see much there. Can we use this kind of robots to replace bees? I think there was some effort at MIT or Harvard a few years ago creating insect-sized robots and letting them fly over agricultural fields. How far that can go? Multi-purpose platforms. I want to fly for chasing birds, at the same time collect data, link that to cloud, download it into the decision-making systems. All that needs to happen together. And economic analysis should include all of that. Then it makes better sense for growers to have a machine sitting there and doing a lot of things that can be done. Transdisciplinary approaches, I think we all know about it. kind of summary of the same thing, but we want to emphasize again payload and endurance. We want to have smaller payload, as lighter payload as possible, still be able to do what we want to do, what we need to do. Calibration in registration and image quality is another aspect that needs to be explored more, because our platforms are lighter, we're moving faster, they may not be always stable. So image mosaicing, as we saw this morning, the mosaicing was not perfect yet. We need to be doing better, because oftentimes we are looking at sub-centimeter or maybe centimeter level accuracy when applying chemicals to kill weed, for example. Can we do that kind of mosaicing accuracy with UAV-based images? Potential adoption model, and now this is my third last slide. Maybe I'll take a minute or two at most. Just to summarize what I think will look like in the future with UAVs. It can be in-house technology for growers, where they do most of the things themselves, or all of the things themselves, or it could be service-based, where I have a company, I provide UAV-based service to growers. With new FAA proposals, this looks promising. How long that takes? Maybe the next presentation will talk about it. What I know about FAA authorization, again, my application is still pending, so I don't have as much information as some of the earlier presenters and the next presentation perhaps. But this is what I believe it takes to get a COA. It may take a few months, maybe longer. We heard this morning 12 months or more. Comprehensive process, description of what, where, and why. Ground school competency for operators, including medical certificate, visual observer, comprehensive reporting, and such. But we're also looking at tethering when possible to do some limited exercise with UAVs. New direction in regulatory arena. Creation of test sites that happened, earlier last year. There are stations in Alaska, North Dakota, Texas, Virginia, I believe, New York, maybe missing one, maybe Nevada. Anyway, there are these larger UAV test stations or centers created, which allows more flexibility for research and development. Recent exemptions to Empire Unmanned in Idaho to do a lot of commercial agricultural applications. Imagine delivery trials, something quite popular out there in the news these days. Proposed regulation, if I understand it correctly, if this regulation is finalized the way it is, I think we don't need COA as long as we meet these requirements. And if I'm accurate on that, I think that will be a really positive direction. Because for a lot of work, except that chemical application work we did with Yamaha, which is 200 pounds or more maybe, a lot of our platforms are less than 55 pounds. So we can do a lot of work with these without COA. If we are under 500 feet, operating in line of sight, daytime, and less than 100 miles an hour. With that, thank you very much, and sorry for taking maybe a few more minutes.